Welcome to today's video on vector addition. Today we're going to talk about vector addition in physics and specifically related to motion and forces. Okay. So what is a vector? A vector is an object that has a magnitude and a direction, and we often represent a vector in physics as an arrow, like so. You might be given a magnitude like 500 newtons or a direction like 600 degrees from the horizontal. Okay, so how do we add vectors? And in this example, what we're going to do is use this force diagram, and we call this a free body diagram. So a force diagram, and we represent forces on that object. So which way is the object getting pulled in different directions? So it's getting pulled by the blue vector up, that'll be FA, the yellow vector FB to the upper right, and the green vector down there to the bottom right there. Okay, so to add vectors, what we actually do is we take each vector and actually join them together. So as you can see, I've pulled FA over there, I've pulled FB over there, and we join them tip to tail. Okay, so the tip of the blue joins with the tip of the yellow there, and the tip of the yellow joins with, the tail of the green. Okay, so tip to tail, the tail means the back, the tip means the front. And so adding all those vectors, we get from the tail of FA to the tip of FC, we get the sum of all vectors, and that is the sum of all forces, which is equal to the net force. And as you can see, if we add all those three vectors together, the resultant force, so what happens to that grey object there is it gets pulled, or a force in that direction. Now, we're going to do something interesting here. What we can actually do is, it doesn't actually matter what order we add these vectors in. So I'm going to add the green vector FC to FB there, add that on the end there, and then add the blue vector onto the yellow vector there. And it actually doesn't matter what order this is in. And as you can see from the start of where we began, so the tail of FC to the tip of FA, we actually get the same sum of forces there. So the same result, doesn't actually matter what order you add these vectors in, you'll still get the same result there, which is a neat little diagram that we can see there. Okay, next little tutorial is on how we add X and Y components. An excellent analogy for this is actually following directions to different places. So what we're actually doing, this is a map of Melbourne, faintly here, from Queen Vic Markets to Fed Square to the museum to the MCG. And we're representing each of these journeys as SA, SB, and SC, or the displacement of A, B, and C of each journey. If we add all those vectors for each of those journeys, we get the S total. And that S total will give us the displacement from the Queen Vic Markets all the way to the MCG, as you can see there. Now, how we split this into horizontal and vertical components is, first of all, we have to see how far east or west we go for each vector. So as you can see here, we go this amount east when we do SA, this amount east when we go from Fed Square to the museum, and this far east when we go from the museum to the MCG. Okay, if we were to go left, we would go west, obviously. Now, the first journey, we go south a certain amount, then we go north a certain amount, and then we go south a certain amount for SC there. So we go down, or a negative X direction, and so forth. Okay, we're going to represent these as SAX, so X will be the horizontal direction, SBX and SCX for all three horizontal vectors, SAY, SBY, and SCY for the vertical vectors there. Okay, usually we represent to the right as positive and up as positive as well. So as you can see, SA plus SB SB plus SC will give us our total ST in the y direction. And similarly for in the x direction, if we add all the how far east or west we go, we can find out how far east or west we are in total. Similarly with the blue vectors for north and south is a great way of thinking of it. So as you can see there, for each of our individual journeys, we can think about how far we've gone east in the x direction for A, B, and C, how far, and that will actually lead to our vector of STX, okay? So as you can see, SA, SB, and SCX will give us our S total X, okay? Now, as you can see, we've gone south for A, then north for B, south for C in the y direction, and then those addition of those vectors, there'll be positives and negatives, cancel out there, and it gets S total y. Now, adding those two total vectors, STX and STY, will actually then get our total vector, or how to get from the Queen Vic markets to the MCG. And we can simply write this as STX or S total X plus STY or S total Y will give us the final vector of STY. So this is the strategy we use for adding horizontal and vertical components. So how do we add these mathematically? So first of all, we'll just take this first example from the museum to Fed Square. We know we can write out what SAX is, the horizontal component, and the vertical component is SAY. And then what we do know is SA equals the actual vector there. That's the one we do know. We can represent that theta as the angle from the horizontal. Now this we use the unit circle angle from the horizontal, and in this instance theta will be negative, because we generally in physics, we represent the horizontal and going anti-clockwise as being positive and clockwise as being negative, just like on the unit circle there. Just as a convention, we use that. So from trig, we know that SAX on SA will be cos theta. So we can then rearrange that to get SAX is just equal to SA cos theta, or SA times cos theta. And SAY similarly will be SA times sine theta. Okay. SA times sine theta, and there are two kind of quick rules to quickly split it into horizontal and vertical components. Okay, so how do we find the total magnitude and direction? Okay, so when we get to the last step, we know what STX is, so the total in the x direction, and we also know what the total in the y direction is. Okay, so STY. Now, there's a couple of things here. We have to find the magnitude and the direction. Okay, so first of all, to find the magnitude, we use Pythagoras. So basically, we write ST, or the magnitude of ST, is the square root of STX squared, so the horizontal component squared of total, and STY squared there. Okay, and that's Pythagoras theorem, and that'll give us our answer for the magnitude. Now the direction, we use tan, or the inverse tan function. We know that STY on STX will be equal to tan theta, and so theta will equal the inverse tan of STY on STX. Okay, so that's a quick, simple way of just finding the magnitude and the direction there, and the direction will be the angle from the horizontal there. Okay. So for this instance, you have a negative STY and a positive STX given given you using north and east as positive, and so theta equals tan minus 1 of ST1, STX, and you'll get a negative angle, which is what you'll expect for this particular. Okay, just as a summary of today's video, a vector is an arrow with a magnitude and direction, so that's from the first bit. When we add the vectors, we add them tip to tail, so just make sure we add them tip to tail, and the final addition is from the tail of the first to the tip of the last. And thirdly, when we split it into x and y components, first of all, we use cos and sine to split the individual vectors into x and y components. The second part B, is to add the x and y components using arithmetic, so how far north and south, how far east and west, to find the x and y totals. And then finally, we combine those totals x and y using inverse tan for the direction and Pythagoras for the magnitude. So that's how we really add vectors in physics, and especially the x and y components bit. That's a great way, or it's a really useful tool to break down 2D vectors there for you. Cool. Thanks for watching today. If it's a long video, I know that. Make sure if you've got any questions, please leave them in the comments below, and make sure as always to subscribe. Thank you. See you later.